Hello, this is Mr. White, recording in 2025 for the lesson for which I will be out of town for one of my College Board mercenary missions. I'm going to just do this in one take. There may be some flubs here along the way. I'm not going to try to polish it up. I trust this will be better than nothing. And of course, I'll hope that students in class will be leaning on each other and using the time wisely to push their learning ahead. All right, on my intro screen here, I have a picture of the couple unit circle clock projects from the recent past that I hope will inspire you to think about what design you want to come up with for your unit circle clock project coming up shortly. It's your design, it's your project. I'm not going to micromanage or tell you what the design has to be. So if you have some artistic inclinations that you want to put on display, go for it. This is one of the prettier designs I've seen over the years, but nobody should feel pressure that they have to have that kind of artistic ability for their project. This one is certainly a more technical design that maybe doesn't have visual artistry as much as a display of some nice calculus and pre-calculus skills. So again, it's your design. You make it what you want it to be. As long as you have a good time with it, I will be satisfied. When I come back into town, we will select paper color. And again, I hope this will just get you thinking about what your design will be. I'll have a variety of papers that you can use, and I'll print a template on it. And you can decide what elements of the template you want. Here I'm paying homage to the student, Eli, who inspired this whole clock project years ago when he got confused about what direction clockwise was. Still have to laugh at that. Also on the intro screen here, you see something, a proof without words of sorts that probably reminds you of something we saw in the last class when I was there live. And again, if you want to pause and look at that and see how this image, without really using any words, demonstrates the summation formula for 1 plus 2 plus 3 all the way up to whole number n. Can you see how this image leads to this formula down here? All right, let me go on to the next slide here. And if you feel like pausing and pondering, I hope you will, whenever I start or engage in an email thread, it makes me think of our summation formulas, specifically that sigma I formula that I just referred to on the previous screen. Okay, so I'm going to go ahead and get into explaining myself there. If you decide not to pause, that's okay, but let me explain. When I start a message, there's one message sent to whoever I'm corresponding with. And when that person replies, as you know, typically you get that person's reply plus a copy of my original message. And then when I reply, there's my new reply plus the last reply I received plus my original message. And you can probably see where this is headed and why it reminds me of our summation formulas. The first message had just one total message in it. The next reply had 2 messages contained within it, and then 3. And of course, the next time you hit reply or somebody hits reply, you get 1, 2, 3, 4. And so again, this reminds me of the summation formula, 1 plus 2 plus 3 plus 4. And if it were to stop there, we could summarize that as sigma from a starting value of 1 to an ending value of 4, and we're just adding the integer I, so that would be the sigma representation or the sigma notation of that series. Now, if this kept going, I will acknowledge that at least the email system I'm most comfortable with eventually stops including every single message, and I don't know what where it stops, but at some point it decides that it can't include every single message, so this analogy breaks down. But of course, I'm hoping that as you go through life, you'll continue to look for mathematical patterns and things that maybe remind you of something we once did in class. Okay, and in a recent class, we introduced a sigma formula that we probably did not really do much of a proof of. And even here, I'm not going to do the most rigorous proof, but I'm going to share with you what's I think is a pretty compelling visual demonstration. We're going to use that word proof lightly, sort of a visual proof that I think for most of us will be pretty convincing. I love this proof. I'd actually looked for a fairly convincing proof for many years and couldn't find one. And then one year when I wasn't even looking for it anymore, I was reading this book by a math professor who I have described as my intellectual man crush, Art Benjamin from Harvey Mudd College in Southern California. And this was from a book he read, or sorry, a book he wrote called The Magic of Math, published in 2015. It's on my bookshelf in my classroom. If you're so curious, you could go find it and look through it if you're interested. Anyway, let me get to what he showed here. Let's say we have a single square here, and of course that could be used to represent the number 1. And because it's a square, I'm going to say it's an area of 1 squared, and just for extra emphasis, because it is a single square, I'll say it's just 1 square of area 1 squared. All right, let's say I draw another square here, and that one is a 2 by 2 square, so its area is, of course, 2 squared. I'm going to draw another 2 by 2 squared, but this time I'm going to split it up into 2 halves. So here's the first half, and I'm breaking it along this edge, and then here's the other half of that same square. So I'm going to say that makes a total of 2 squares, each with an area of 2 squared. Let's draw in a third square, 3 by 3 square. Has area 3 squared, and I'm going to draw 2 more of those. This time I don't need to break any squares in half. So 3 total squares of area 3 squared each. You could probably guess where I'm going with this, and of course, it goes without saying, if at any point you want to pause this, ponder it a little bit, see if you can anticipate where I'm going with it, of course I would welcome you to do so. All right, so did you know that I was going to draw this square next? You probably knew it was going to be a 4 by 4 square. Exactly where I drew it maybe wasn't quite as obvious, but there's one. Here's another 4 by 4 square, and here's another 4 by 4 square. And I'm sure you know I'm going to draw a fourth 4 by 4 square, but this time I'm going to break it in half, just so it fits neatly right there. Let's go ahead and do one more. Let's do this 5 by 5 square. Maybe you're getting the hang of this, and you can probably tell that I'm not going to need to break this one in half, right? I'm going to just fit 5 by 5 squares right where you knew I would put them. 1, 2, 3, 4, 5. And it is worth pausing and kind of looking and seeing if you could convince yourself as to why these fit so neatly, why it makes such a consistent pattern. How do I know for sure that the next iteration, the 6 by 6 squares and the 7 by 7 squares, how do I know they'll continue to fit neatly into this overall encompassing square pattern? I'm just going to add this in here. Again, I added a 5 by 5 square, and then I added 5 total of them. So let me stop there. Of course, I could keep going to whatever number of levels I want, but what's the total area of this entire pattern up to this point? Well, look at how, what's the size of this overall square, isn't it? 1 plus 2 plus 3 plus 4 plus 5. So the length of that encompassing square is 1 plus 2 plus 3 plus 4 plus 5. That's the length of the square side, but then of course I'm going to multiply it by itself. That's another 1 plus 2 plus 3 plus 4 plus 5. So would you agree with that? Again, pause and make sure you agree with what I'm doing here, that the sum of those smaller squares is equal to the overall 1 plus 2 plus 3 plus 4 plus 5 quantity squared. And if you agree with that, let's move on. This first row here, what is that in sigma notation? Well, isn't that really 1 times 1 times 1, 1 cubed? Isn't this 2 times 2 times 2, 2 cubed, 3 cubed, 4 cubed, 5 cubed? This is a sigma of I cubed from the lower bound, I equals 1, to the upper bound, I equals 5. And we are claiming in this line that it equals 1 plus 2 plus 3 plus 4 plus 5. In other words, sigma I from I equals 1 to 5. And of course, that whole quantity is being squared, right? So I will square that. And here's where we're at. We've got a sigma I cubed, and it equals the sigma I being squared. And we already have a formula for this. It was on the opening screen of this lesson, and we also went over it in our previous lesson and came up with a little more of a convincing argument for why that formula is n times n plus 1 over 2. But again, we're going to square that whole thing. And I just used the letter n there, right? That means that I'm now generalizing this first sigma. I'm not just going from 1 to 5. I'm going from 1 to an upper bound of n this time. And again, leave it up to you to decide if you feel like this has been a convincing enough argument that this would hold true for higher n values. Anyway, you can leave it like that. In the previous lesson, we probably kind of demonstrated a pattern that suggested this formula was true. We didn't really come up with anything terribly convincing. I think this is a more convincing and very visually pleasing argument as to why that formula is what it is. And if you want, I'm content to leave it the way it is on the screen right now. If you want, you could square those factors individually. You could FOIL it all out if you wanted to. I can't really think of why that would serve us well, but that is our sigma I cubed formula. To really rigorously prove it, you'd need to do something called a proof by induction, or at least that's the kind of standard way of proving such things. And if you're curious what that means, it's something that, for better or for worse, is sometimes covered in pre-calc courses. We did not cover it. If you're curious what a proof by induction looks like, of course, I'd welcome you to do a web search. It's not that hard. We just didn't make time for it in our studies. All right, so that's our sigma I cubed formula. If you're still wondering, what about sigma I squared on a later lesson, I'll have some visual proofs that I've come across over the years that I think are pretty remarkable. All right. And just one more reference to the earlier slides. That's my student Eli, the same one who I make fun of for getting the direction of clockwise mixed up. But he's a very bright dude, and he ended up going against Art Benjamin in a backgammon tournament back in 2019 and ended up beating him. And Dr. Benjamin was very gracious and congratulating him. And anyway, I love that anecdote that a former student of mine went up against an intellectual who I greatly admire. All right, if I were there live in class, we would do this free response question from 2003, page 5 in our latest packet. We wouldn't do the whole thing, just part A, and the main reason for that is because notice it's a related rates problem, and I know that makes a lot of students nervous. So if you feel like you could use a little bit of quick practice on related rates, go ahead and do that one on your own. I don't know if we're going to make time for that when I get back. Probably not. So again, if you want just a little bit of quick practice, try that one out on your own. Go ahead and do a web search for that year and that question if you want to check your answers. You can try parts B and or C if you want. I'm going to go ahead and tell you that we haven't formally covered that content. So as the little note says, part B may look very doable. I'm going to tell you again, technically we have not covered that part. So I'll let you come to that conclusion on your own if you're willing as to why it initially looks easy, but then turns out not to be doable with the techniques we've studied so far. All right, and if I were in class, we might also possibly do this warm-up, this do now. I'm not going to do it right here because I want to keep this video relatively short. I don't intend to go on for a full 95 minutes here with this recording. And also there's a recording of a very similar example from in our chapter 4.2 webpage. And in fact, the very first video on that page, if you look at example number 3 in that video, it looks very stylistically similar to the one that's on the screen right now. So that's the content from our last lesson. You had some homework problems that looked kind of like this. If you had trouble with these, of course, work with your neighbors to work through that and or check out my videos and just know you're responsible for it. So I hope you're feeling okay with that skill, even if you don't entirely know why we're doing such monstrous exercises like this. The good news is that part of the objective of this lesson right now is to get a little insight as to why am I putting these torturous creations in front of you. We're going to try to make sense out of an expression like that today. All right, so let me go ahead and display the even answers from the last homework, which was just trying to get our feet wet, get us used to sigma notation and what it means. And one thing I hope I made clear in class is that even though we eventually came up with some summation formulas, we're not obliged to use them. And in fact, some cases we can't use them. So we could have used the sigma notation formulas for question number 2 here, exercise number 2, but you'd have to be aware that we had a starting value, a lower bound of 3, not 1. And the formulas that we came up with had a starting value of 1 down here. So we'd have to find some way to deal with this. And here's the overall observation you should make is that there's not that many terms in this series. If we're starting at term k equals 3 and we're ending at term k equals 6, that's just 4 terms total. 1, 2, 3, 4. So the point here was rather than try to deal with some formulas, just write out the 4 terms, add them up, and get your total of 50. That was all you're expected to do for this exercise. My note here says, notice that not all series converge. We may or may not have introduced that verbiage in the last lesson, converging versus diverging series. Let me just explain real quickly. All I mean by that is the type of series that we're going to be using the type of sigma notation series that we're going to be using are going to be ones to find area under a curve, the finite area under the curve. And the idea will be that as we cram more and more rectangles under such curves, that the sum will converge to, will get closer and closer to the actual area under the curve. However, notice that this, in contrast, is a diverging series. We just went up to an upper bound of 6, and this number got up to 50, and you can kind of tell that if we had gone up to 60, let's say, that would have been many more terms, and this number would have been a lot bigger, and if I'd gone up to 600, this would have gotten even bigger. That's what we'd call diverging, and a big part of our time in BC Calc or Calc 2 in college is dealing with series and being concerned with whether they converge or diverge. All right, so also notice that in number 6 here, again, it's a very short series, just 4 terms total. So even though we do have some formulas that we could have used, if you're just adding up 4 terms, just simply write them out, add them up. The objective of this exercise was just to make sure you know how to interpret sigma notation, that you know what it means, and you weren't supposed to be using the summation formulas yet. I want to point out that for number 4, exercise number 4, not only would it not have been a good idea to try to use a summation formula, but You can't. We don't have a summation formula for 1 over j or 1 over I. We had a sigma formula for sigma of a constant, sigma I squared, sigma I cubed, but we did not come up with a formula for sigma of 1 over I, or in this case, 1 over j. So again, it wasn't even an option to use a sigma formula. You really had no choice but to add up the three terms and just do it that way. Okay, so with all that being said, let's go ahead and get to the bulk of today's lesson. We're going to apply these skills, sigma, and I'm even going to sneak limits in there. Technically, applying the limits is more for our next lesson, but I don't know, I can't resist. We're going to go ahead and throw the limits in there too to find area under the curve. When you do the sigma up to some finite upper bound, you just get an approximation of the area under a curve, so to speak, and then when you slap on the limit, you get the actual area, the exact area. So that may not mean a whole lot to you right now, but stay tuned. I'm going to explain what I just said on the following slides. Okay, I'm sure I've already shown this probably multiple times, but I just can't resist. I'm so unjustifiably proud of this. GeoGebra time. All right, maybe I find that more funny than I ought to, using 30-something-year-old pop culture references. But GeoGebra time, let's go ahead and switch over to GeoGebra. We're finally here at the moment where we're going to start really doing this for real, other than me just giving you previews of something coming up. We're at that moment where we're going to take curves such as the graph of this function right here that I just have entered in by default. Nothing particularly special about it. But as we may have already discussed, we have several ways we can cram rectangles under or about this curve. Right now I have something displayed called a right sum. And as I may or may have not already discussed previously, the reason it's called a right sum, or more specifically a right rectangular sum or a right Riemann sum, named after the German mathematician Riemann. The reason it's called a right sum is because notice that the upper right corner of each rectangle is lying right on the graph of that parabola. The upper right corner of each rectangle lies on that graph. Of course, if I had something called a left sum, it would be the upper left corner that lies on the curve itself. And as you know, the link to this GeoGebra construction is contained in the lessons document, and I highly encourage you to play around with it, either right now or as you go through the lessons here. We also have upper sums, where every single rectangle is a little bit too big and peaks up above the actual curve, gives me a little more area than I really want. And we also have lower sums, where every rectangle is a little bit too small. And the truth is, if we're going to do the limiting process, if we're going to cram 100, 1,000, 1,000,000, if we're going to approach infinitely many rectangles crammed to the curve, the truth is we don't really care which one we use. We could use any one of them and they'll all give us the same answer. By the way, I'm going to save trapezoidal sum for some other day. But let me go ahead and display all of these at the same time. And if I had a small number of rectangles under there, let's start with the minimum number of rectangles, 1, you see that I've got some very different sums. Let me go ahead and slide this back over to right sum. We got some very different sums, but as I increase the number of rectangles, keep an eye on those 3 numbers and keep an eye on how those numbers are graphed here as well. Look at how those sums are being graphed as I increase the number of rectangles down here along this axis. All those different sums, which started off as quite different numbers, are starting to converge towards the same number, or to use other vocabulary that we're more used to. They all have the same horizontal asymptote as I take n and drive n up towards infinity. So I'm going to repeat what I said a moment ago. If we're going to use the limit process and take the limit of n as n approaches infinity, I could use a left sum, a right sum, a middle sum, an upper sum, a lower sum, and all of them will approach the same asymptote. All right, so with that big setup, let's go ahead and get into this. All right, as you can see here, I'm going to do a variation of a problem of an example from our textbook. And in our textbook, if you're curious to compare and contrast, this is from page 256, or 2 to the 8th power. 256. All right, the textbook had some finite number of rectangles. I think it said use 5 rectangles if I recall, but I want to change it to a more general n rectangles. And whereas the textbook did an upper and a lower sum, or maybe it was a left and a right sum, I just want to focus on one of those. We're going to do one type of approximation, and we're going to do a right Riemann sum. And again, named after the mathematician Bernard Riemann. You can call it a right sum or a right Riemann sum. Either one is fine. But I'll prefer to give respect to the guy who's credited with developing this process. Anyway, we're going to use n rectangles to find the right Riemann sum of the area of the region lying beneath this graph of this parabola and the x-axis on the interval from 0 to 2. And of course, I am asking that you write this down in your notebook and add any additional notes in addition to what I write on the screen here. Write down something that will be useful to you later. This is a fairly complicated process. It's a lot, so please be active in your listening and your participation. Pause, talk to your peers around you as needed. So in addition to writing down this basic info, let's start with the picture, and I'm going to strongly urge you to be generous. Give some generous space to this picture. Whereas I appreciate that sometimes students have a preference to write small, I'm going to suggest you make this picture span the width of your notebook page. So let's make it reasonably tall. If this were a standard notebook page, I don't know, I'd make it 6, 7, 8, 9 lines tall, and then again, span the entire width of your page, or at least most of the width of your page would be my suggestion. And let's draw this parabola. So negative x squared plus 5, we don't need a calculator for that. We can use our basic pre-calc skills. We know what the basic y equals x squared parabola looks like with its vertex at the origin, smiling. We know the negative sign is going to flip it upside down to make it frown. We know the plus 5 is going to translate upward. So with those skills in mind, let's draw a parabola let's again, make it nice and wide because we're going to cram a lot of rectangles under here. All right, so because that got translated up 5, I know that this is going to be 5 here, and I'm going to give a little bit of thought as to where that x-intercept is. Looking at my equation here, if I mentally set that equal to 0, I can tell that the positive x-intercept is going to be at square root of 5, right? Plugging in square root of 5 for x will give us a y value of 0. So I'm going to put square root of 5 here, and I know that square root of 5 is somewhere between 2 and 3. Going off the top of my head, I think it's 2.23 or something like that. Anyway, I bring that up to say that if we're only interested on the interval of 0 to 2, I want to make sure I get that 2 properly located. I don't want to put the 2 over on this side of square root of 5, so I'll say it's somewhere right about here. Of course, the 0 is right here, and let's draw some representative rectangles under here. Because we're doing a right sum, I'm going to make sure that the upper right corner of each rectangle lands on the curve. So there's my first rectangle with the right corner on the curve and upper right corner on the curve. Here's my second rectangle, also with its upper right corner on the curve, and I'm going to draw at least 3 before I just do a dot, dot, dot. I'm going to draw one sort of in the middle. You'll see why here shortly. I'll draw one rectangle in the middle. I'll do another dot, 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 and then I'll go all the way to the end, and I'll draw the very last rectangle, and I usually like to draw the one more right before it. And let's go ahead and label these rectangles. Let's say this first one is rectangle number 1, so I equals 1. The second one is rectangle number 2, I equals 2. I equals 3, we get the idea, and so on. And what should I label the last rectangle? Well, there's n total rectangles, right? So that's rectangle I equals n. And how would I label the one before it? Well, if the last one is n, then the one before it should be n, whatever n minus 1 is, right? And what about this one in the middle? Well, that's my general kind of representative rectangle. I want that to be able to represent any of the rectangles under this curve, from the first one to the last one. So I'm going to say that's rectangle I equals, well, I. I'm just going to call it rectangle I. And it's understood that I is going to be between as low as 1 or as high as n, or any number, any whole number in between. All right, let's now give some thought as to what the width of each rectangle is, or the base. I'm going to use those two terms interchangeably, the base of the rectangle, the width of the rectangle. I don't know why, I just sort of subconsciously flip-flop. Don't really care as long as we understand what each other means and we use these terms consistently here. I'm talking about how wide is this? Now, the truth is with any Riemann sum, there is no hard and fast rule that all these rectangles have to be the same width. It is allowable, generally speaking, that you can have one rectangle be really wide and then the one right next to it could be much thinner. But we really don't see at this time, for what we're doing right now, there's no reason to go out of our way to do that. So let's go forth on the premise that we're going to have all these rectangles be the same width. And so this width, or base, again, using those terms interchangeably, I'm going to say the base of each rectangle, and I'll use the letter I just to kind of emphasize that that could be I equals 1, that could be I equals n, or any number in between. The base for all these rectangles is going to be what? Well, pause and think about it. This is where traditionally, historically, I start to lose some students. So again, don't feel bad to pause, ask your neighbor around you. Make sure you get this point, because this is where some students start falling off the train. I want you to think of how wide the total interval is. The interval we're concerned with goes from 0 to 2. So we're talking about a total interval that is 2 wide, 2 units wide, and it's being split evenly among n rectangles, right? So think about it. Every single rectangle has a width or a base of 2 over n. Okay, I could put 2 over n right there. And again, sorry if I'm being too redundant, but that width is 2 over n, that width is 2 over n. Every single rectangle has a width of 2 over n if we're going forth on the assumption that they all have the same base or width. Okay, I next want to focus on what is the height of each rectangle. That will vary from rectangle to rectangle, clearly, right? All of these rectangles have different heights. And before I get too intent on just the height, I need to first focus on the x values. And here's why. I'm going to call this x subscript I. And wouldn't I take that x value, and in order to find this height of the rectangle, wouldn't I need to find that x value first and plug it into this equation? Isn't that what's going to give me the height of the rectangle? Isn't that what's going to give me the y value for that rectangle, right? So our goal is to get the height of each rectangle, but let's first focus on the x values. All right, and let's kind of build up to a pattern here. Let's look at the x value that I would plug in to find the height of rectangle number 1. So that height right there. How would I find that x value? Well, the x value, x subscript 1, is merely going to be that base, right? So isn't x over 1 going to be just 2 over n? But what about x2? That's going to be the x value I would plug in to find the base of, or the height of rectangle number 2. That's talking about that total x value. So again, I really want to emphasize, I'm not just asking about the base, I'm asking for what's the distance from the y-axis over to this edge of the rectangle. So that's 2 rectangles wide, right? All right, let me write it down here. x2 is going to be 2 over n, but it's 2 rectangles wide, so I'm going to multiply that times 2. And I could simplify that to 4 over n if I want, but I'm going to choose to leave it unsimplified. How about x3? Isn't that 3 rectangles wide? That's the x value. And again, sorry for being so repetitive, but I really want to distinguish the difference between the x value versus the width of just a single rectangle. The x value here is 1 base multiplied by 3 rectangles. All right, so just to really accentuate the pattern here, I'm going to put a 1 here. And I hope you see the pattern here, and you can kind of anticipate, what am I going to say about x subscript I? I hope you can kind of see what it's going to turn into, right? So all of these x values have a 2 over n to start, so I'll go ahead and keep that going, 2 over n. But then we're multiplying by however many rectangles over we are. x1 had a 1 here, x2 had a 2 here, x3 had a 3 here, right? So wouldn't xi be I rectangles over? And wouldn't I just multiply by whatever I is? And here, I'll go ahead and say, if I want, I'll go ahead and call that 2i over n. And just to really kind of make something click here, that hopefully makes sense, let's talk about the very last rectangle. Wouldn't xn, by that same logic, be 2 over n times what? Times n, right? And you see how the n's divide out, and you end up with 2, and you go, oh, well, that makes sense. That's what I expected to get here. Okay, so the x sub I value is 2i over n. Again, I'm being very repetitive, I know, but really emphasize, notice the base and how it's similar and different to x sub I. And I'm stressing this because so many times over the years, students put one of these when they should be putting the other, and it tells me that they're not really understanding the process. They're probably just sort of memorizing a pattern without fully understanding it. So this is a big deal. All right, why did we want to find the xi value? We ultimately wanted to plug it in and find the height, didn't we? So that's where we're finally going to use the f of x equation here. So let's turn our attention to what is this height? That height, I'm going to say that's the height of rectangle number I, or height subscript I. Isn't that going to be the y value I get when I plug x subscript I into our function equation, right? We're going to take this xi and we're going to plug it in this equation. So let's do that right now. If f of x is negative x squared plus 5, then f of xi is going to be negative xi squared plus 5. And I have an expression for xi. So let's plug that in. That's going to be negative we're going to plug that 2i over n in. And of course, the role of the parentheses there is important. And what's the area of a single rectangle going to be? Area of a single rectangle, and I'm just going out of my way to make clear, I'm not talking about the total area under the curve, so to speak, yet. I'm just going to say the area of a single rectangle, whatever rectangle I want, whatever I value I want, that's going to be base times height, isn't it? So isn't that going to be base 2 over n multiplied by this height that we just found, negative quantity 2i over n all squared plus 5. That's the area of the single rectangle. Now let's talk about the area that we get when we add up all the rectangles. So to be clear, that's not going to be exactly the area under the curve because we've still got these little gaps here that we haven't really discussed or accounted for yet. But if I make n big enough, if I can cram enough rectangles under there, those gaps will presumably become quite small, and they'll get even smaller as n approaches infinity. This is where sigma comes in, right? So sigma from the first rectangle all the way to the last one. Now that's the area of the entire, well, the area of all the rectangles under the curve. That's the right Riemann sum area. So let's call that S for sum, and then right sum. All right, so we're not quite done yet, but this is sort of a milestone here. And this is, again, where I welcome you to pause and make sure you're soaking this in and kind of talk to somebody if you need to get some clarification on something. This is a good milestone for this problem. And I can't help but go back to a previous slide and say, what about that do now that I was going to do if I had been there with you in class? Hey, look at that. Here's the big reveal that the thing that looks a lot like the exercises from your previous assignment, doesn't that look in structure? Well, doesn't that look a lot like the sum we just came up with? The only difference is that here I have a limit on there, right? Here I've already applied the limit, and you can already hopefully kind of see the connection that that limit is what's going to drive the number of rectangles up to infinity, and that's what's going to give us our exact area. So that's technically something for another day, but I'll go ahead and say it right now. That's the exact area under the curve. And by the way, if I haven't already mentioned it, this phrasing area under the curve is a bit problematic. It can be confusing when the curve dips underneath the x-axis, then it doesn't really feel like the area under the curve. This is a common phrasing, problematic as it might be. We'll talk more about it later. But for right now, I'm going to go ahead and indulge and use that phrasing. This is the exact area under the curve. What makes it exact is when you apply the limit. For today, we're really going to focus on the sigma notation without the limit, but it's not a big step to take for you to slap the limit on there if you feel like just kind of working ahead a little bit. All right, so I hope this is all making sense. I love this stuff. I find it quite exciting still after all these years of teaching it. Let's go ahead and go forth, and I'm going to speed up a little bit here because presumably we've kind of practiced the skill already from the previous assignment. Even if we didn't really know what the broader context was before, in our last assignment we were practicing how to do this. So let me go ahead and proceed. I'm going to say that right sum equals, I'm going to split this up into two separate sigmas. I'm going to say one sigma is going to include this distributed to this, so it'll be that first term. Let's focus on those two terms for the moment. Just cover this up for just a moment. So I'm going to take a bit of a big leap here. I'm going to say I really would like to just have sigma of I squared and then bring anything else to the outside, any other constants to the outside. So there's my I being squared. So I'm going to put I squared, and as I often say, if you need to do this in smaller steps, do what makes the most sense to you. But I'm going to take this 2 over n. This 2 over n is being squared also, right? So isn't this 2 over n squared giving me 4 over n squared? But then I'm going to multiply by a third 2 over n to give me 8 over n cubed, and then that negative sign will give me a negative 8 over n cubed. Of course, pause, make sure you agree with that. All right, and if you do agree with that and are ready to move on, let's now turn our attention to the second term. I'm going to say that makes me think of our sigma constant formula. Even though n in some sense is a variable, for the purposes of sigma, when we're dealing with the sigma, it's the I that is varying. The I is what varies from 1 to 2 to 3 all the way up to n. So when we're dealing with sigma, you may treat any n factors as constant. Now, looking ahead, when we then are dealing with the limit, that's where the n becomes variable. But for right now, for purposes of a sigma, we may treat sigma as a constant. And you have a choice. When you distribute 2 over n times 5, you can just leave that as 10 over n right here. Or if you prefer, and I really have no preference, I probably flip-flop back and forth about evenly. If you prefer, move that 10 over n to the outside and just leave a 1 on the inside. Again, I made a big deal of saying we can treat it as a constant, and you can bring constant multiples to the outside of sigma. So there's the plus. And now it's time to use our summation formulas. All right, what was that formula for sigma I squared? Wasn't that n times n plus 1 times 2n plus 1 all over 6? And how about sigma constant? Wasn't that just n times whatever the constant is? N times constant, in this case, n times 1. We'll go ahead and keep these other constants here. All right, and technically, depending on the context, depending on what I'm asking of you exactly, this is the first point where I could call myself done, possibly. If I was just asked to find a right sum, there it is. That's our right sum as a function of n, the total number of rectangles. And again, you could plug in n equals 10 rectangles. You could plug in n equals 100, n equals 1,000, similar to what you were doing on our previous homework assignment. All right. So kind of recapping up to this point, make sure you're clear on the difference between base I being 2 over n, the x value being 2i over n. When we plug that x value into f, that's what gave us the height. We multiplied base times height to get the area of a single rectangle, and then we used sigma to add them up, and we used our summation formulas to give us this final answer. All right, so there may or may not be some times where we discuss a desire to simplify this expression or not. I think the most obvious thing to do is to let those n's divide out, and we could do some simplification on the other term as well, but I'm not going to do that at this point. I think just to bring this example to a close, let's just convince ourselves of what we just did and whether or not this worked. Let's take that expression and type it into our calculator. I've already done that. All right, here it is. And I'm going to use the table in our calculator. I'm going to go to second table set, and I'm going to change that independent variable to ask and go to our table. And let's type in 10. Let's say I'm cramming just 10 rectangles under that curve. The area of just the rectangles should be 6.92. So now I'm going to return to that GeoGebra construction and see how that does or does not fit into our scenario here. All right, you can see I've already pre-entered in our function, negative x squared plus 5. I already set this to be the right sum. I've already set the number of rectangles to be 10. And look at that right there. We can see 6.92, just as our calculator said. 6.92 is the area of just the rectangles. We can tell that this is going to be a little bit too small. As I cram more rectangles under there, I should expect that right sum to increase. So let's drive the number of rectangles up to 100. It looks like now the area of just the rectangles is 7.29-ish. So I'll put 100 in here in the calculator table, and just like GeoGebra said, 7.29. What if I went up to 1,000? I'll set the limit here to 1,000. I'll just go ahead and drag all the way there. I see that I'm up to 7.3293. I come over here, I put 1,000. If I just put a really big number, let's put 1 billion. Sure looks like this is going to level off at 7 1/3, right? And again, I think I'll show some restraint and wait until the next lesson to formally take the limit. But if you're feeling capable of doing so, I urge you to go ahead and do it. Go ahead and take the lim as n goes to infinity and prove to yourself that the limit of this right sum is going to be exactly 7 1/3, which is 22/3. Okay, I don't think you'll find it too hard if you want to go ahead and do that step. All right, and it turns out again, 7 1/3 is what we're going to propose as the exact area under that curve from 0 to 2. All right, I hope you're finding this kind of interesting. Year after year, I always find this stuff fascinating and still can't quite believe that it works. And that was our big example for today. I hope you're still with me here. I'm going to finish off with a couple other much lighter examples, so they shouldn't take us nearly as long. All right, I'm going to admit that part of me contemplated wrapping up the video right at this point on the assumption that maybe I've exhausted your attention span. But year after year, the exercises in the textbook that look like the ones on the screen right now cause enough confusion where I feel obliged to address those confusions. So if you want to take a pause from the video and try some exercises on your own, of course, do so. But when you're ready, and also, of course, try these exercises as well, or the similar ones assigned to you. And if you don't have any trouble with them, then you don't need to watch. But let me go ahead and address the confusions here that I typically see. At the risk of sounding like I'm blaming the victim, I'm going to say that I usually find that I don't think students read the instructions very carefully, or maybe they just don't, maybe they read them and just don't understand what's being asked of them. We are being asked to bound the area of the shaded region, for this one on the left, by approximating, keyword approximating. By no means are we going to find that exact area. I don't even know the equation for this curve. There's no way to find the exact area. We're going to approximate the upper sum and the lower sum. We're going to use that verbiage instead of left and right sums, although we could have asked that as well if we wanted to. But we're going to focus on the upper and lower sums. And here's the part that students seem to miss. We're only using rectangles of width 1. We are not going to cram a bunch of rectangles under here. We're only going to cram, well, it looks like 4 rectangles under here of width 1. So let's go ahead and do that. And let's start with the lower sum. Okay, so because this is the lower sum, it needs to just sneak up and just touch the underside of this curve there. Goes no higher. That's the lower sum. It turns out you could also call that particular rectangle a left sum rectangle, right? Because it's the left corner that touches the curve. But for the next rectangle of width 1, if it's going to be a lower sum, it turns out it's the right corner that's going to touch first. So again, if I'd made that rectangle lower, it's not touching the curve. And if I'd gone higher, that's starting to look more like an upper sum, isn't it? So that's what a lower sum rectangle looks like. The next lower sum rectangle of width 1 will look like that. And then the last one, notice the last one I don't really have any room for. I mean, I'll draw that right there, but doesn't it just bump up against the curve right away, so it really has no room to grow? It's got 0 height. All right, so those are my lower sum rectangles, and I'm going to label that as S lower. Yes, looks like slower. S lower equals, let's see, that first one was 1, 2, 3, 4 units squared plus another 4 plus 2. And then the last one I didn't have any room for, plus 0. So the lower sum is going to be just 10 units squared. No units are specified, so if you just put 10, I'll allow it. Some people are in the habit of putting u squared for units squared. That's fine too. All right, so assuming that made sense, let's go ahead and turn our attention to the upper sum. We'll call that S upper, supper. And this time we're going to do a sum that goes up and just barely encapsulates the curve there. So an upper sum is going to go up this high, right? And then the next upper rectangle will go up this high. Again, the first upper sum rectangle had its right corner touching, so it was also a right sum rectangle. But then the next one, its left corner touch, so it's a left sum rectangle. And then this one, and then this one does have room to grow. And I'm going to say it goes up there. It looks like I could stop right there, but that's not quite an upper sum. I need to go a little bit higher. And this is where, again, we're just approximating. So I'm going to have to come up with a number there and just estimate and be comfortable doing that. The first upper sum rectangle was 1, 2, 3, 4, 5, as was the second one, right? So that's going to be 5 plus 5. And the next one was a nice clean 1, 2, 3, 4. And the last one, sometimes students are a little uncomfortable with this. They're not used to being asked to approximate. I'm going to tell you that's what's called for here. It would be inaccurate to say 2. That's not quite upper sum. So I'm going to estimate that that's 2.3. And anything that's just in that ballpark, I would count correct. I'm not looking to try to ding you for not getting the exact same approximation I did. So 5 plus 5 plus 4 plus 2.3, by my count, is 16.3 units squared. Okay, and just to provide some context of what did we just accomplish here, we're basically done. We did what was asked of us. And just to provide a little further context, what was the point of that? The point is that those two, the upper and the lower sum, bound the actual sum, the actual area. So if I use the letter S to represent the exact area, or the actual area as I'm calling it, the actual / exact area, the point is that S is bound between S lower, which was 10, and S upper, which was 16.3. Now, that may seem like a bit of a wide window, and of course, if we wanted to narrow that window down and get a better sense of what the actual area is, we could have maybe done rectangles of width 1/2. We could have done more rectangles that were slimmer and gone that route. But this is just a very conceptual problem. If we get that answer, then we're going to assume you got the idea that we want you to get here. All right, assuming that all made sense, let me go ahead and delete this so that I can clear some room for the last example here. All right, and in contrast to the example we just did where we were just provided a picture but not an equation, this time we are provided a picture and we'll gather some information from that. We're also provided an equation too, so we're going to use our calculator for this one. It doesn't explicitly say it here in the instructions, but we're going to. And we're going to use upper and lower sums to approximate the area of the region using the indicated number of subintervals of equal width. So what they're referring to when they say the indicated number of subintervals is they're saying, look at the picture, just count. Notice that for every unit along the x-axis, for example, between 0 and 1, notice that that single unit has been divided into 1, 2, 3, 4 rectangles, as is the next unit, because they're of equal width. We're going to be consistent there. So doesn't that mean that every rectangle is of width 1/4 or 0.25 if you prefer? And also I want to point out that we were instructed to use upper and lower sums, but we have a strictly increasing curve here. This curve is going straight uphill. So what I want you to notice is that when you have a strictly increasing curve, let me start with the lower sum. The lower sum, those are the sort of light purple rectangles. That's the one that's going to go this high, right? Is the lower sum a left sum or a right sum? Well, just using your eyeballs, isn't the lower rectangle bumping in at its left corner into the curve? So in this case of an increasing function, the lower sum is also a left sum. And again, I really want to emphasize that's just for increasing curves. And also the upper sums. Aren't the upper sums the ones that are going to be these here? And isn't it the right corner there? The next upper sum, it's the right corner. The next rectangle, upper rectangle, it's the right corner that's landing on the curve. So again, strictly for increasing curves, the upper sum will be a right sum as well. Now, I'm just going to give a very quick lip service. That would all be reversed. If you had a decreasing curve, then the lower sum would be a right sum as well, right? And the upper sum, let me draw it over here just to get it out of the way. Wouldn't the upper sum be a left sum? So this is something you do not need to memorize. You just draw the picture, you just look with your own eyeballs and make that connection about whether left corresponds to upper or lower. You don't need to memorize that. All right, let me go ahead and get that off the screen and continue with the example at hand. So let's focus on what are the x values we need to plug in to do this. Again, I'm going to do the lower sum, the lower slash left sum first. So let's start with that one. Because it's a left sum, I'm going to start at x equals 0. And then the next rectangle, to get the next one, I'll go to x equals 2.25. And then the next one will be 0.5 for this rectangle right here, ... And the very last lower rectangle, I'll be plugging in that x value at 1.75. So I'll turn to my calculator now, where I've already entered in that function, and I'm going to make use of the table. There are several ways you could do this, and if you think of another way that you'd rather do this, be my guest. I'm just going to show you one way that you may not think of and that I'd probably use myself. I'm going to go to the table. I still have it set, by the way, if I go to table set, I still have it set to independent variable asking. I don't have it automatically filling in. I'm going to go back and change it back to auto. But now when I go to the table, I notice that the x values are jumping by 1, and I don't want the x values to increment by 1. I want them to increment by 1/4. So one more time, I'm going to go to table set, and I'm going to set this delta table. Let me go ahead and set the start value. I want to start at 0. And delta table, I'm going to set that to 0.25. 1 is what we'll normally have there and want 99 point something % of the time, but this is a rare time where I want that to be 0.25. Now when I go to the table, I see all the heights that I want listed in the Y1 column. So let me drag that on here. And remember, I wanted the heights that correspond to all these x values, starting at 0 and ending at 1.75. So what I would write on my page is that the very first base times height. Now base, let's remind ourselves, base is not the same as x value. The width slash base is not the same as x value. The width or the base is just 0.25. So the very first rectangle has a base or width of 0.25, and I'm going to multiply that times the first height, which was f of 0, or 2, right? Now I could add all these base and heights separately, but I want to be efficient here. Because they all have the same base slash width, let me move that parentheses over and just add all the heights in here at once. Let me add the next height in there, plus 2.5. Let me add the next one in here, and I'll go by the standard College Board rules of 3 decimal places. 2.707 here, plus 2.866, plus 3, and then 3.118, plus 3.225. And finally, 3.323. Just double check, I should have 8 total rectangles. 1, 2, 3, 4, 5, 6, 7, 8. So again, rather than do base times height, base times height, base times height, I just did the base a single time and just multiplied by all the heights, kind of mentally figuring I could distribute that base times height if I feel like it. And this is not the most elegant way to go about it, but I could just type that whole expression into the calculator. There are other ways to do it that may feel a little more fancy or efficient. Again, be my guest if you want to try another way, but I'm just going to enter that all in as I have it written there. All right, just double checking, making sure I typed these all in correctly. And since there's only 8 rectangles, I just found it easier to just do it this way. If this had been like 800 rectangles, I'd try to find some sigma notation way of doing it, but I'm just going to do that and hit enter. And that is our approximation, 5.685, 5.685. So I'll put approximately 5.865. That was an approximation. And let's see, that was the lower slash left sum. Technically, I'm only accountable for the lower sum, but I'm going to choose to acknowledge that that was also a left sum. So I'll put S lower, which in this case, for this increasing curve, was also the left sum. All right, let's now consider the right sum, the upper slash right sum. Good news is it's mostly the same process. The only difference is I've got to shift one space to the right. For this upper curve here, this very first upper rectangle, I'm going to use this same x value that I used previously for the second rectangle. This time I'm using it for the first right slash upper rectangle. And then I'll use this number instead of using this for the third rectangle. I'll use it for this second upper slash right rectangle, and so on. I'll keep using the same x values all the way up until the 1.75. That will be for the second to last rectangle. And for the very last rectangle, this time I'll use the 2. So maybe you're noticing that most of these heights are going to be used for both sums. The only difference is that 0 is used on the left slash lower sum, and 2 is only used on the right slash upper sum. All right, that was a lot of words. I hope it made sense. Of course, stop, pause it, and let it sink in if need be. What it means for me here is I'm going to use these values this time. And just for expediency, because I can, I'm just going to copy my, my lower and left sum. I'm going to erase that first rectangle that I'm not going to use this time and just move this over. And let's add in that last height that I am going to use for the upper slash right sum. So that's 3.414. Again, this is our upper, which is what we're asked for, but we notice that's the same as a right sum in this case for our increasing curve. I'll come back here, copy this. I'll go back to the beginning and delete that first number. I'll go back to the end and add in there 3.414, close it off, hit enter, and 6.038 is what we want, 6.038. 6.038. So again, we know that the actual sum is somewhere in between that lower left sum. I'm going a little bit beyond here. I don't have to say this. I was not asked to provide this information, but just to make it add in that little extra context. The whole point of upper and lower sums is to kind of bound the number that we're really wanting. The actual sum is somewhere in between, but the answer to our question that we were asked is 5.865 for the lower left sum, and then 6.038 for the upper right sum. All right, the last thing I'm going to leave you with is a bit of a teaser of things to come. When we get more sophisticated and really master this limit and summation, finding area under the curve, so to speak, and get some more advanced techniques, we're going to be able to find the exact area more quickly for under curves like this. Right now, I have to point out that because we do not have a sigma formula for square root of I, we have sigma formulas for constants and I squared and I cubed, but we don't have a formula for sigma I. So right now, we don't have the means to find the exact area here. Later on, when we get a little more sophisticated, we'll find that the exact sum turns out to be 4 plus 4 square root of 2 over 3. And when I type that into calculator, it turns out to be 5.886 rounded to 3 decimal places, which again, affirms that we were in between the upper and lower bound, the upper and lower sums. All right, so again, that's a teaser for some weeks down the road. This will be to come later. All right, thank you for your attention. I hope you're doing all right, proceeding with your learning in my absence, and I look forward to being back with you soon. Bye-bye.